Okay, let's jump right into the example problems uh, related to the video that I posted yesterday. The first couple of problems are still going to look directly at executing a hypothesis test, but we have the slight shift from considering hypothesis testing relating to a population mean and now looking at hypothesis testing relating to a population proportion. So let's look at this first example. Let's say we have a sample of 150 recorded blood donations. And in our sample, we find that 82 of these donors were blood type A. Now, from external information, we know that it's believed that 40% of all individuals have type A blood. And so we want to test this hypothesis at the 10% level of significance. So let's start by summarizing the information that's given to us. Firstly, our sample proportion, p hat, this is what we observe, 82 successes or 82 type A's in 150 individuals, and that gives us a sample proportion of 0.5467. Now, the belief under the null hypothesis, or P naught, is that this is going to be 0.4. And the moment you identify that you're testing a hypothesis about a proportion, you should think, in addition to needing P hat and P naught, if you want to calculate your test statistic, you're also going to need some estimate of variance, which in this context is sigma naught squared, and that quantity is calculated as P naught times 1 minus P naught. So in this case, 0.4, sorry, tablets being persnickety, 0.4 times 0.6, or 0.24. And if we take the square root of that, because this is the quantity we really need, we get 0.4899. So those are all the pre-calculations. Let's look now at doing the hypothesis test. So our null hypothesis is that 40% of individuals in the population are type A, and the alternative, no specific directional statement is made, nothing about it being more than 40% or less than 40%. So if you don't find any directional information, your alternative will just be a complete negation, in this case, not equal to 40%. So there's our null and our alternative hypothesis. Now we can calculate our Z observed statistic, which is P hat minus P naught over sigma naught over square root of n. So just subbing in all these values that I've already calculated. And if you punch all of this into your calculator, you should get a test statistic of 3.667. Now, two-sided alternative means our p-value is given by both the area to the left of negative 3.667 and the area to the right of 3.667. And we can use the normal approximation here. This is valid because our sample size is at least 30. If you are trying to test something relating to a proportion and you don't have a sample size of at least 30, we don't have any other way of doing that. So that would kind of just leave you stranded and you would have to say no calculation is possible. But because this condition is satisfied, we can calculate our p-value as 2 times the normal CDF at the negative value of the test statistic. And if you go and plug that into norm CDF on your calculator, this will give you 0.00012, or if we ultimately round this, say, to 4 decimals, you'll get a p-value of 0.0002. So to reach our conclusion, we want to take this p-value, compare it to alpha, which in this case is 0.1, a 10% level of significance. So the p-value is less than alpha, which means we are going to reject the null hypothesis. What does that tell us? You always have to make sure that you ultimately write down or state a conclusion in the context of the original problem. If we reject the null hypothesis, then this tells us our sample evidence suggests that the population does not have 40% of people that are type A. Because the alternative is two-sided, you want to be careful to, say, make a statement that it's more than 40% or less than 40%, because we didn't test it in a specific direction. So looking at what we observe, right, our p-hat, it does look to be more than 40%, but you want to avoid making that part of your conclusion unless your alternative specifically was directional in one way or another. So with a two-sided alternative, your conclusion is going to be restricted to something that just says it's not equal to 40%. Any questions about this problem? I'll give a few seconds. Okay, let's look at our next example here. This time, we're looking at an airline who believes that 5% of their customers qualify for some executive travelers club. They take a random sample of 500 customers, and of those, 44 would qualify. So our sample proportion is 44 of the 500, which in this case is 0.088. They believe that it should be 5%, so that'll be our belief under the null hypothesis. And again, we know we're going to need some kind of estimate of variance. So for a proportion, we have to calculate the sigma naught squared quantity, which is p naught times 1 minus p naught, or in this case 0.05 times 0.95, which is 0.0475, and so square root of that gives us 0.2179. So there are all our pre-calculations. Now we can go and set up our hypothesis test. This airline believes that 5% of individuals qualify. But we want to test, in this case, we get a specific directional alternative. We want to test that perhaps the true proportion exceeds the 5%. So this time, our alternative would be that P is greater than 0.05. Now, this doesn't affect how you calculate your test statistic. The Z observed still calculated in the same way. Just plug in these numbers that we've calculated. And if you go and evaluate Z observed, it's pretty darn close to 3.9. So now, when you're evaluating your p-value, we only want the area to the right of Z observed. To the right, because we had greater than under the alternative. So our p-value in this case, if your alternative is that the population quantity exceeds the value under the null hypothesis, you will calculate this as 1 minus the normal CDF at 3.9. And the normal CDF at 3.9 is 0.9995. So we end up with a p-value of 0.0005. What does this mean here? We're evaluating this test at the 1% level. So our p-value, if we compare it to the alpha of 0.01, p-value is less than alpha. Small p-value, small likelihood that the null hypothesis is true, so we reject the null hypothesis. What do we conclude here? Well, this time our alternative was directional, so in the conclusion, you can make use of that directional property. We can say the sample evidence suggests to us that more than 5% of customers would qualify. So I'll give a few seconds again if anyone has a question about this problem, but you should, I hope, feel here that nothing dramatic has changed moving from testing a hypothesis about a mean to testing a hypothesis about a proportion. You just have to calculate the sigma naught quantity that goes into your test statistic. Okay, let's move on then. The next problem we're looking at is an illustration of the relationship between constructing a confidence interval and performing a hypothesis test. If you watched the video I posted yesterday, you would have seen there that we should have consistency between the conclusion we reach with the confidence interval and the conclusion we reach when we perform a hypothesis test. So in our setup here, we are given a 95% confidence interval for the true average warpage of laminated sheets. So we're looking at how much they warp. Someone collected a sample of size 15, constructed this 95% confidence interval. But someone else says, well, I didn't really want the confidence interval. I wanted to test, is the true mean equal to 2? Now, the only thing you have to pay attention to is you want to make sure that your confidence interval is, the standard two-sided interval, and your alternative hypothesis also needs to be two-sided. You need that consistency for these results to be applicable. But if they are both two-sided, that means what you see in your confidence interval will be consistent with the conclusion reached from the null hypothesis. So a 95% confidence interval that we have, that will be consistent with a hypothesis test at the 5% level of significance. So the level of the confidence interval and the level of the test, they should add up to 100%. those are the comparable situations. So in this case, the value under the null hypothesis is 2, but that null value is not inside the confidence interval that was calculated. And so that means the value under the null hypothesis is implausible. So mu naught is not a plausible value. And if it's not plausible, what would we expect to do? We would reject the null hypothesis at the 5% level. So because the value under the null hypothesis here is not inside the confidence interval, we would reject the null hypothesis. Now, what would happen if we wanted to do this at the 1% level of significance? Well, the 95% confidence interval now is not directly applicable. So we have two options. One of them is we can go and perform a formal hypothesis test at the 1% level. Our other option is, for the 1% level, we would want a 99% confidence interval. But whether you go and calculate a p-value and compare it to a level of 1%, or whether you construct a 99% confidence interval, those should result in the same conclusion. So I'm going to go the confidence interval route only because that's, the concept I'm trying to illustrate here. So we want to find a 99% confidence interval for the true population average mu. Now, to do that, let's look at the setup we have here. We know that we have a normal distribution, but if you read the problem beyond that, the population variance is unknown. So this means that we need to use a t-distribution for this confidence interval. So our formula here is x bar plus or minus s over square root of n, t of alpha over 2 and n minus 1 degrees of freedom. Now, at first glance, we need a lot of information here that doesn't seem to be available. Like if you just read the problem setup, the only piece of information here that seems to be available is the sample size n. But we can take the observed confidence interval and we can reverse engineer that to solve for a few of the other quantities. So let's first consider our 95% confidence interval, which in this case would mean the t-value that was used, alpha here would be 0.05, so alpha over 2 would be 0.025 and 14 degrees of freedom. So on your calculator, you would use t inverse. The area would be equal to 0.975 and the degrees of freedom would be equal to 14, and you would find a t-value here of 2.145. Also, because the interval for the mean is symmetric, we know that the sample average is just the midpoint of the confidence interval, which in this case turns out to be 1.88. Of course, we know our sample size is 15, so we can now use, say, the formula for the upper bound, x bar plus s over square root of n, and the appropriate t-value, and we can solve for s. That's the only unknown quantity here. If I plug in all the quantities I know, and I know I can trust all of you to figure out how to solve that equation. It's not a difficult equation to solve, and it tells us that the standard deviation that was used here is 0.1264. So this now gives us everything we need to construct our 99% confidence interval. X bar plus or minus S over square root of n times, now we would need T of 0.005 and 14 degrees of freedom. So here you would use T inverse area equal to 0.995 and degrees of freedom equal to 14. And this gives us 2.977. So if we now substitute in all the information we have, we get a confidence interval, 99% confidence interval that spans the range of values 1.783 through 1.977. So what is our conclusion? Our value mu naught of 2, that's still not inside this interval. Right, so this tells us at the 1% level of significance, mu equal to 2 is still not plausible. So we still reject the null hypothesis at the 1% level of significance. I'll give a few seconds here if anyone has a question. Okay, our last two examples for today looks at the question of multiple testing. So just to recap, there are sometimes instances where you either collect multiple samples and you want to test a hypothesis in each of them, or maybe you have one sample, but you have multiple hypotheses you want to test in that sample. And the moment you're doing multiple tests, you need to make sure that you're using an appropriate significance level or an appropriate alpha value, because multiple testing increases the probability that a type 1 error happens at some point. So let's say that we are doing m different tests on independent samples, and each test is carried out at a level of 1%. Part A here asks, if we have 5 independent samples and we're testing a hypothesis in each of them at the 1% level, what is our new overall significance level? Or equivalently, what is the probability of committing at least one type 1 error? Well, we refer to this as alpha star, overall significance level, or probability of at least one type 1 error. And this is simply given by the formula 1 minus alpha, in this case to the power m. So alpha is the individual test level, m is the number of tests. So if I just sub in these quantities, then I'm just trying to evaluate this expression. And if we do this, we'll get 0.049. So roughly 5%. But what this tells us is if we are performing 5 individual tests, and they're each done at the 1% level, then it's still pretty close to 5% the chance that at some point we make a type 1 error. So our overall level is no longer 1%, it's much closer to 5%. What about if we were doing 10 different tests? So this just changes the value of m, and in this case, if you calculate this, you'll get 0.096. So now we're pretty close to 10%, right? If you were going to do 10 tests that are assumed independent, each one at the 1% level, then overall you now have closer to a 10% chance of at some point making a type 1 error. So how quickly does this escalate? Part C here asks us to determine for what value of m will this probability be 0.5 or larger. So we want to know when is alpha star going to be at least 0.5. Well, we know in this case we're doing our individual tests at the 1% level. So rearranging things a little bit. I just subtract 1 on each side and then multiply by a -1. So that's why the direction of the inequality changed. Now I can take logarithm on both sides, and doesn't matter what base you use for the log here. What does matter when you're solving for m is we're dividing by log of 0.99. And remember, log of a fraction is negative. So I'm dividing by a negative number here, which again changes the direction of my inequality. But if you then evaluate, regardless of base that you use, log of 0.5 divided by log of 0.9, that gives us 68.96, or 69 different tests. So even if you are doing each test at a 1% level, if you are doing 69 tests like this, then there's a 50% chance that you will make at least one type 1 error, and it could be more than one, right? So, so you end up having to be really cautious in your approach. And you may be asking, well, when do people actually test 69 different hypotheses? Well, that happens in a lot of different real-life applications. For example, there are these studies that look at RNA strands, and compare different pairs across samples. And so there you're in a situation where someone is doing thousands of hypothesis tests. And so they have to be very careful about the level of significance they use, because they don't want to have a very inflated risk of committing type 1 errors. So let's look at our last example here. Again, we have someone who wants to do K hypothesis tests independent, but wants the overall level to be 5%. So this researcher is saying they want their alpha star to be 5%. If they are doing 8 different tests, what level should they use for the individual tests? Well, if you solve for alpha from the alpha star equation, you get 1 minus alpha, in this case to the power 1 over m. And if we then sub in what we know, 1 minus alpha would be 0.95, and we want to raise that to the power 1 over 8. Again, if you just go and plug this into your calculator, I'm going to keep a few decimals here, and you'll see why in a minute. But this tells us our individual tests, we have to go and do at roughly a 0.64% level of significance. If we are doing 8 tests and overall we want 5% level, then the individual tests need to be happening at a 0.64% level. And this is if we can assume independence. What about if we do not have independence? Well, if we do not have independence, then our adjustment looks a little different. if we don't have independence, then we just take the overall level we want and we divide it by the number of tests that we're performing. And I'm just realizing I'm writing M in my solution here, but it was called K. So just note here, K and M are the same quantity here. So if I want an overall level of 5% and I'm doing 8 tests, then this approach says my adjustment should be that my individual tests are performed at a, roughly 0.63% level. So you'll notice here that the difference isn't that big. Some books make a pretty big deal about which approach you use to make an adjustment. Like, can you assume independence or not? The bottom line is, when you cannot assume independence, right, this is the more conservative approach. Because it guarantees that you'll have an alpha star of no greater than 5%. But the individual test level that you reach under this approach is generally only a tiny bit smaller than the level assuming independence. So if you're ever in a situation like this and you have questions about whether independence is reasonable, just use the more conservative adjustment, because it's not going to be that radically different, and you have a safeguard built in against deviation from the independent hypothesis assumption. So that's everything I have for today. I will take a few questions, but I'm going to turn off recording here for the video that I'll post for anyone who's not able to join us live.